So if we're dealing with potential energy, any form of potential energy is always associated with some sort of force. For example, what types of potential energy have we looked at so far?
Spring mass and gravitational.
We've got the spring potential energy, we've got a gravitational potential energy. Each one of those is associated with a force. You've got the spring force, you've got the gravitational force. And there are other forms of potential energy we're going to look at later as well. In 7C, we're going to look into electrical potential energy, which is related to an electrical force. In fact, we're even going to be looking into that a little bit in 7A, at least with regards to graphing it. But every form of potential energy is associated with a force, because potential energy can be thought of as just the energy that you store, the energy that you save up and keep when you do work using a force. For example, if you lift up an object, you're acting against the force of gravity. You're doing work against the force of gravity, so you're storing gravitational potential energy. If you compress a spring, you're doing work against the force of the spring, so you're storing spring potential energy. If you take two charged particles and push them close to each other, let's say they're opposite charges, so they repel, you'd have to do work to push them close to each other. You're acting against the electrical force, so the work you're doing is stored as electrical potential energy. Any sort of force where you can do work against that force in a way that is stored up counts as a potential energy. Any questions on that so far? And since this is all based on the idea of work, in all of these cases, we can say that let's say you're doing work to cause the potential energy to change. And let's say you're doing work to increase the potential energy. You're doing work and you're storing it as potential energy. Maybe you're lifting an object and putting it on a shelf. Maybe you're compressing a spring and then tying it off. In that case, the work you're doing equals the change in potential energy. And we're assuming no change in kinetic energy here. Let's just assume that you're pushing something so that it moves at a constant speed. How do we usually write out work?
Force over the change in distance.
Yeah. Or I would say force times distance, because we're multiplying, not dividing. But it is a force applied as the object moves some distance. So if you're applying a force to an object as it moves some distance, then the product, force times distance, tells you how much the energy changes. And if we're assuming you're moving it at constant speed, you're applying a force just to keep it moving without speeding up or slowing down, then the change is only potential energy. We're not changing the speed because we want to focus on just one change here. That force you're applying, the applied force, if you want to move it at constant speed, that applied force has to balance out precisely some other force. Because if the forces don't balance out, then the object's going to get faster or slower. But let's say you're lifting an object. You're acting against what force when you do that?
Gravitational.
Right. You lift an object, you're applying exactly enough force to cancel out the force of gravity. And that's true whether you're just holding the object still or raising it at a constant speed or lowering it at a constant speed. In all those cases, you're applying exactly enough force to cancel out gravity because you're not changing how fast it's moving. No acceleration means no net force. So the force you're applying is just going to be the exact opposite of some naturally occurring force, which we can write as negative F. So the force you're applying is the opposite of the force associated with this change in potential energy. And with that, how would you solve that for force?
Force would equal the negative change of potential energy over a change of distance.
Yeah. if we just divide both sides by negative delta x, the force you're applying, or rather the natural force, the force that you're acting against is negative change in potential energy over change in x. So change in potential energy over change in x is the force you're applying. The opposite of that is the natural force that you're acting against, the force of the spring or the force of gravity or whatever. And more formally, we should write this as a derivative. Change in potential energy over change in x suggests a change over some certain interval. We've got some distance traveled. It costs some amount of energy to do that. But formally, this shouldn't be the change over the change. This should be the derivative, the instantaneous rate of change. So really the way these should be related is force equals negative derivative of potential energy with respect to x. But we can say that's approximately change over change. Any questions on that so far? And we can also do that a different way. If you want to solve for potential energy, what's the opposite of a derivative?
An integral.
Yeah, so we could write this in integral format also. If you take the opposite of both sides and then integrate, you get a formula for potential energy. So potential energy can be defined as, in fact, this is really what potential energy is. Potential energy is the integral of negative force dx. So if you have a formula for force with respect to position, you can take the opposite of it and integrate and get a formula for potential energy. Or if you have a formula for potential energy, you can differentiate and take the opposite, and that gives you a formula for force. Just two different directions of looking at the same relationship here. Any questions on that so far? So let's take a look at how this applies to graphs. If we have a graph of potential energy versus position, let's say something like this. And this isn't necessarily any specific type of potential energy. Let's just say we've got some sort of potential energy whose graph looks like this. How would you interpret force on the graph of potential energy? What does the derivative tell you about the graph? If we're talking change in potential energy over change in x, potential energy is the vertical, distance is the horizontal. So change in potential energy over change in x, what is that describing about the graph? Yeah, that's the slope. So the slope of the graph is really what's telling you the force. So this change in potential energy over change in x, it's really just saying force is the negative slope of the potential energy graph. So if we can find the slope of the potential energy graph, the exact opposite of that is the force. And magnitude in this sense is a good way of looking at it as well. Magnitude just means absolute value for vectors. So the magnitude of the slope, that is the absolute value, equals the amount of force. The positive and negative sign is just describing direction it's pointing. And the difference between these two ways of writing it, the change in potential energy over change in x suggests we've got some change in x. Let's say this distance is the change in x. Let me make that a little larger, actually. So let's say we mark off a change in x. This x value has a potential energy associated with it. This x value also has a potential energy associated with it. If we draw out a straight line linking those 2 points, x1 and x2, Anyone remember from calculus what we call that line, linking 2 points on the curve? It's close to the tangent line, but it's not exactly a tangent line. But yeah, this would be the secant line. So the secant line is a line linking these 2 points on the curve. Straight line from a point to a point on the curve through another point on the curve, and we keep going. And the slope of that would be change in potential energy over change in x, in the sense that you've got a change in potential energy, you've got a change in x. You take the delta potential energy divided by the delta x, just rise over run from point to point. And that would tell you the slope of the secant line. The thing is that slope of the secant line, delta energy over delta x, that's useful as an average. This tells you the average rate of change over this interval, in other words, the average force. But it's not exactly the force at any one of these points. If we compare individual points, like at this point exactly, the slope is more like this. And then a little further, it gets steeper and steeper and steeper and steeper and steeper. There's going to be one point on that graph where the slope is the same as the slope of the secant line. But at other points, we have different slopes all over the place. So we can't really use the secant line as an exact value, except at one single coincidental location. Instead, we want to look at the tangent line, which would be the slope at one single point. For example, at this point, if you draw in with a straight edge, ideally, a straight line matching the curve as close as possible at and near that point, this would be the tangent line. And for the tangent line, the slope is the derivative. So that's the difference in notation here. D whatever dx means the slope of the tangent line at that point. Delta whatever over delta x means the slope of the secant line from point to point. It's the difference between an average value over some interval versus the exact value at that one point. And they can both be useful. If you're looking for something that broadly describes a process over some interval of space or some interval of time, the average rate of change, the secant line, is usually more useful. But if you want to know something that's going on at a single instant in time or a single location in space, the tangent line is really what we're looking for. And that would be the derivative. But as we take these 2 points and bring them closer and closer and closer and closer together, the secant line gets closer and closer to the tangent line, which is why we define different derivatives in terms of limits in the first place. Any questions on all that so far? So let's take a look at some specific tangent lines here. I'm going to take out the secant line for now, and let's just look at some tangent lines. Because the tangent line is really the best description of what's going on at a single point, a single location. So at this point, we've got this tangent line. What do you notice about the slope of that tangent line? At this location, how would you describe the slope of that tangent line?
It's close to 0.
It's pretty close to 0. What does that tell you about the force? If the force is opposite of the slope, if the slope is pretty close to 0, what does that suggest about the force?
The magnitude is pretty small.
Yeah, we've got a very small magnitude force, a very weak force. Also, it looks like the slope, would you say the slope here is positive or negative?
For the tangent line, I'd say it's positive.
Yeah, this is a positive slope tangent line. As we move to the right, the positive x direction, we're also increasing potential energy. So a positive change in x is associated with a positive change in potential energy. Change over change is positive over positive, so we get a positive result. So at this point, the slope is positive. What does that suggest about the force?
The force is attractive.
Attractive and repulsive aren't always the right words to use in cases like this, because we're not really, we haven't really talked about what this force is. Maybe it's two objects attracting and repelling each other, or it might just be one object experiencing forces in different directions. Yeah, I would just say the force is negative here. Force is in the negative direction, in the sense that the force has to be the opposite of the slope. If the slope is a small positive number, the force is going to be a weak negative force. And what negative means is going to depend on the situation. If we're just talking about like an object, let's say we got a falling object. Maybe this is something kind of like gravity and we're talking about the vertical direction. In that case, the negative direction would presumably mean downwards. If we're talking about horizontal motion, maybe negative means to the left. If we're talking about a spring, maybe negative means in the direction compressing the spring. Or if we're talking about particles attracting and repelling each other, negative would mean towards each other. And the reason why we describe negative as towards each other is if particles move towards each other, what happens to the distance between them?
It gets smaller.
Right. Particles moving towards each other are shrinking that distance between them. That counts as a negative change in the distance. So if a force is trying to attract the particles, if the particles are attracted to each other, that is a force attempting to shrink the distance between them. So we describe that as a force in the negative direction. So for an interaction between two objects, a negative force means a force trying to attract them together. A positive force means a force trying to repel them apart, in the sense that repulsion would increase the distance between them, a positive change. So negative and positive for forces just represent directions. What directions each one actually means depends on the circumstances and how we're setting up the coordinate system. But usually we like to use a positive force to represent a force trying to increase some quantity, such as distance between objects, and a negative force is a force trying to decrease some quantity. Any questions on that so far? One important thing to notice about this, if we actually draw in that force as an arrow, as we sometimes do, so often on graphs like this, we draw out the force as an arrow on the graph. Like at this point, the force is in the negative direction and fairly weak. So we'll draw a small arrow pointing to the left. What about at this location? What's going to be different at that point?
It'd be a stronger magnitude, so a larger arrow.
Yeah. This is a much steeper slope. If we draw a tangent line here, it's a fairly weak slope. Tangent line here is a much steeper slope. So at that point, because the tangent line is so much steeper, we've got a strong force. Steep tangent line, steep slope, means a strong force, relatively speaking. And also this is still a positive slope, so we still have a negative force. So that'll be a force in the negative x direction and stronger. So we would draw that on the diagram as a larger arrow. And then in between, it's going to be maybe medium strength. So we could draw in several arrows, getting larger as the graph gets steeper and therefore stronger forces. What about if we take a point, let's say right here? What do you notice about the force or the slope at this location? At this location, the slope is
It's a negative.
yeah. The fact that the function is decreasing as we go left to right indicates that this is a negative slope and therefore a positive force. So the force at this point is going to be pushing in a positive direction. Presumably about the same steepness as maybe this one, so those will be about the same size arrow. And notice that all of these forces we've got so far, they're all pointing towards what location? Like these ones all seem to be pointing to the right. These ones all seem to be pointing to the left. They're all pointing towards what though?
The turn point towards like when the slope is 0.
Yeah, if we have this, it looks like we have one point here where the slope is 0. If the slope is 0, what does that tell you about the force?
There is no force.
Right. We have this one location here where there is no force. Maybe there's one force and it happens to equal 0, or maybe there's several forces and they all happen to cancel out. But at this location, the net force is 0. So we would call that equilibrium. Equilibrium literally just means a location where the forces all cancel out. So at that point, there's no force at all. Are there any other equilibrium locations here? Anywhere else where the slope is 0?
I think at the top of that curve on the left.
Yeah.
Then also at the bottom of the curve on the left.
Right. Any maximum or minimum, if you go back to calculus, any maximum or minimum is a location where the slope is 0. You want to find the max or min, you set that you take the derivative and set it equal to 0. Because at a max or min, it has stopped going up and is about to start going down. Or it has stopped going down and is about to start going up. Either way, the slope at a max or a min is going to be 0, a flat tangent line. So we know at any of those maxes or mins, the force is going to be 0. So those all count as equilibrium. But we've got some other different kinds of equilibrium. If we actually draw in some forces here, in this region, we've got a negative slope, so we get a force to the right. In this region, what do you notice about the slope? In this region here, slope is as we go from left to right, the function seems to be increasing. So we would say the slope is positive. And if the slope is positive, then the force has to be negative. So in this region, we've got a force to the left. Meanwhile, in this region, we've got a negative slope. So we've got to have a positive force. Any questions on those forces so far? And if we now compare these equilibrium points, if you take a look at this equilibrium, like if you're exactly at equilibrium, you can stay there forever. There's no force at all. But what if you're a little bit to the left or to the right of that equilibrium? Like let's say you're at this equilibrium and you move a little bit to the right. What are the forces going to do to you? Yeah, if you move a little bit to the right, the forces in that location push you to the left, back towards equilibrium. Or if you move a little bit to the left, you encounter forces that push you to the right. So that's also back towards equilibrium. All the forces in the neighborhood of this equilibrium are pushing back towards equilibrium. So if you start there, you'll stay there forever. If you move a little bit away, you'll be pushed back towards equilibrium. So we call that stable equilibrium. What about the forces near this equilibrium point? Like this is equilibrium. If you start here, you'll stay there forever. But what if you go a little bit to the right of equilibrium? What's going to happen? Those are going to push you in which direction? Yeah, more to the right. So if you go a little bit to the right of this equilibrium, you get pushed further away from it. Or if you go a little bit to the leftward forces push you further away from equilibrium. So this would be called an unstable equilibrium. If all the forces near equilibrium are pushing you away from equilibrium, It still counts as equilibrium technically, because if you start there, you can stay there forever. The force at that location is 0. But this would be an unstable equilibrium. And then this one also has forces pointing towards it. If you move a little bit to the left, you get pushed back to the right. If you move a little bit to the right, you get pushed back to the left. So this would also be a stable equilibrium point. Any questions on the difference between those so far? So if you have a handful of objects and you just throw a bunch of objects into this situation and let them move around, where would you probably expect to find most of them? If you just throw a bunch of objects into this scenario and maybe some of them keep moving around, some of them eventually come to a stop, where would they eventually settle down to? If you just consider what forces are pushing them around. Yeah, all the objects are, if they're able to move around and they have enough energy to get there, they'll eventually end up at stable equilibrium. And the thing is, as they're passing through stable equilibrium, let's say you're approaching stable equilibrium. As you approach it, you're losing potential energy. So what else is going to happen? If you lose potential energy, then presumably you're also going to, presumably you would increase kinetic energy. So as you're going towards a stable equilibrium, you're losing potential energy. And if it's a closed system, you're also gaining kinetic energy. So you're getting faster and faster. So you're actually going to pass through stable equilibrium going at tremendously fast speed. As soon as you pass it, you're now gaining potential energy. So you'd be losing kinetic energy and slowing down. So an object in motion is going to be passing through stable equilibrium at very fast speed. In fact, the fastest it can be going under those circumstances. But if it's an open system, if the particles are gradually losing energy due to, let's say, friction, maybe it's going to be oscillating and then oscillate smaller and smaller as it loses energy and eventually settle down to the lowest energy state it can reach, which would be stable equilibrium. So if objects are not losing energy, then they're just going to be continuing to move. If objects are gradually losing energy, usually due to friction or air resistance, they'll eventually settle down at the stable equilibrium locations. So in any real world scenario, if you know where the stable equilibrium points are and you want to find objects that have been lost somewhere, look at the stable equilibrium points. And that's where you can expect to find objects that have settled down into a stable location. Any questions on that so far? All right. Then let's try out an example with some actual formulas then. Let's say we take a look at gravity, for instance. Do you have any formulas for gravity? If we wanted to graph some of these for gravity. Any equations for, potential energy, right? Potential energy of gravity is mass times gravity times height. So if we were to graph that, and keep in mind mass and gravity can be treated as constants. As an object moves around, its height is the only thing that's going to be changing. So if we were to graph that, y versus potential energy, what would that graph look like? If you're just graphing a constant times the variable. If the output equals a constant times the input, that's always going to be what shape of graph? Yeah, that's always going to be linear. And even more specifically, since we don't have plus another constant, what's the intercept of this going to be? What's a point that we know this goes through? Yeah, that's always going to pass through the origin, 0, 0. So regardless of what we call the variables, whenever you have output variable equals input variable times a constant with no other modifiers, that's always going to be a straight line passing through the origin. And what is that constant, that mg? What does that tell you about the line? Yeah, that constant is just going to be the slope of the line. So potential energy is going to be, for gravity, the potential energy graph is going to be a straight line passing through the origin whose slope is mg. For instance, let's say you have a 5 kilogram object. If we treat gravity as about 10 meters per second squared, 5 kilograms times 10 meters per second squared would be 50. So you'd have a straight line with slope 50 through the origin. So that's just going to look like something like that. So that would be our potential energy of gravity graph, potential energy versus height. And keep in mind that this axis, even though it's drawn horizontally, it represents height. So this means higher heights, this means lower heights. And 0 is kind of arbitrary here. You might say 0 is ground level, so these would represent locations above ground and these would represent locations underground. Or maybe 0 is the top of a building, and these would be locations above the roof, and these would be locations below the roof. Or maybe 0 is sea level, or wherever. You can choose any height you want and call it y equals 0 as a reference point. So positive potential energy just means you're higher than the reference point. Negative values for potential energy are possible. They just mean you are below the reference point we're talking about. Also, if potential energy's slope tells you the force, what do you notice about the slope of this potential energy graph? It's got a positive slope. And also, does the slope change from point to point? No, it's a constant, right? It's got the same slope everywhere. That's the defining attribute of a straight line. So this graph has a constant positive slope, which means, what does that tell you about the force? It's going to be negative. And also, since the slope is a constant amount, the force will also be a constant amount. A constant negative force. That is a force that's always in the negative direction, specifically the negative y direction, and a constant strength. So what this tells us is that the force of gravity is a constant amount of pull, and it's also always in the negative direction, specifically the negative y direction. And what does the negative y direction mean? If an object is moving, yeah, the height is decreasing. It's moving downwards. So negative y direction means downwards. So all this is really telling us is if you're dealing with an object that's experiencing a force of gravity, the force of gravity is constant and pulling downwards. And note that this ties in very closely to potential energy. The force of gravity is pulling downwards. What happens to an object's gravitational potential energy if it moves downwards? Moving downwards means its potential energy is decreasing. So the force of gravity is pointing from a high potential energy zone towards a low potential energy zone. As a general rule here, we've got, if you've got a high potential energy zone, in this case, just a high altitude, and a low potential energy zone, the force associated with this potential energy is pointing from high potential energy towards low potential energy. And of course, that only specifically means the force associated with that potential energy. There may be other forces involved, and those don't have to follow this rule. For instance, we've got high potential energy of gravity, low potential energy of gravity. Force of gravity is pulling down. But there could, of course, be other forces acting on the object in any other direction you want. Like an object doesn't have to move down just because there's a difference in potential energy. The difference in potential energy just signifies that that one force is pulling in that direction. Any questions on that so far? And if we actually do the calculation here, like if you have a graph, you could just, how do you usually find the slope of a graph? The direction the object moves. The object could actually be moving in any direction. Ultimately, force doesn't tell you which direction an object is moving. Force just tells you acceleration. Force equals mass times acceleration. So a force doesn't make an object move, a force makes an object accelerate. It changes the velocity. It doesn't cause the velocity in the first place. Force is negative, it's pulling down. If force is negative, it's pointing up. If we're specifically talking about y values, yes. So for the usual way we set up the y-axis is upwards is positive, downwards is negative. The usual way we set up the x-axis is positive is to the right, negative is to the left. But it really varies from situation to situation. If you've got some other direction of travel, you could just choose a direction to call positive and a direction to call negative. So which direction is positive and which direction is negative is really just a matter of the coordinate system we're using. It's just that for commonly used coordinate systems, there are conventions that we just usually use for that coordinate system. Likewise, if you've got two objects interacting with each other, towards each other is the negative direction because that's decreasing the distance. That's a negative change. Away from each other is the positive direction because that's a positive change. That's trying to increase the distance. Any other questions on direction so far? Positive and negative force, it's all about direction. There is, for any given moving object, there's a direction we're going to call positive and a direction we're going to call negative. If we're talking about if force is pointing upwards, in this case, the force of gravity is pointing downwards because that's the direction from high potential energy of gravity towards low potential energy of gravity. But in any situation, any type of potential energy, the force associated with that type of potential energy will always be pointing from the high potential energy zone towards the low potential energy zone. In fact, that's really what this negative signifies. Derivative of potential energy is talking about how the potential energy changes. The negative sign means in the direction towards lower potential energy, in the direction of decrease. For example, here, the force is pointing in the direction of decreasing y, the negative direction. And even though we're drawing the y-axis sideways, this still means upwards and downwards. So these arrows to the left really mean force pointing in the downwards direction. We're just drawing it on the horizontal axis. And since it's the same slope everywhere, these arrows would all be the same size. They're all the same strength of force, same magnitude. We could even calculate that. We know that the force is the negative derivative of potential energy. If you actually take the derivative of this, what would be the derivative of mgy if we're using y as the variable? So derivative of mgy. Yeah, should just be mg. Mg is a constant, so you can pull that out. We're left with mg times dy dy, and dy over dy is just 1. So the derivative of potential energy is just mg, in other words, the slope of the line. And the force of gravity is going to be the opposite of that derivative, so negative mg. And note that mg is a constant. Negative in this context means the downwards direction. So the derivative also agrees that the force of gravity should be downwards and a constant amount, proportional to the mass. Any questions on that so far? Then let's try applying the same approach to a spring. What's our usual formula for potential energy of a spring? Spring potential energy equals, what's our formula for that? Yeah, 1/2 kx squared, where k and 1/2 are both constants. So that's just a constant times x squared. And so what would that look like on a graph? Yeah, we should expect a parabola whose steepness and curvature depends on how strong k is. So there's our, should make that more symmetric. So there's our potential energy graph. And at any single location, we could analyze the forces involved by looking at the steepness. So at this location, in fact, on this entire side of the parabola, what do you notice about the slope? Yeah, if we were to draw a tangent line anywhere over here, those tangent lines would all have positive slope. So this entire region has positive slope. So what does that tell us about the force? Yeah. So force is negative. So that would mean in the negative x direction. In the context of a spring, we usually treat the positive x direction as stretching and the negative x direction as compressing. So if you move this, the end of the spring so that it is stretched, you get a force back towards the compressive direction. In other words, back towards equilibrium. And what happens to the slope as we move further and further out on the graph? If you're looking at a larger and larger and larger x value, what do you notice about the slope? Yeah, a steeper slope means a stronger force. So near equilibrium, we're going to have a fairly weak force. And then further, we're going to have a stronger and stronger force. What about on the entire left side? What's going on with the slope and the force over here? Yeah, we've got a negative slope. So that means we're going to have a positive force pointing in the positive x direction. And again, it's going to be stronger force when we have a steeper section of graph, weaker force if we've got a less steep section of graph. And at the origin, at the vertex of the parabola, there's no force at all because the slope is 0. It flattens out at that point. So these would be the forces involved. At each location, we've got a force whose strength is just how steep the slope is, and whose direction is towards decreasing potential energy. So all of these forces on this, the spring force is pointing inwards towards equilibrium because equilibrium is the lowest possible potential energy. We could even analyze this using the derivative as well. Derivative of potential energy is going to be, how would you take the derivative of 1/2 kx squared? When force is positive, yeah, a positive force would be trying to push the spring further out. A negative force would be trying to pull the spring further in. So if you stretch the spring, you've changed x to a positive number, but the force is going to be negative trying to shrink it again. If you compress the spring, you've changed x to a negative number, but the force would be positive trying to expand it again. In this case, the force is always pointing towards equilibrium. In general, any force associated with a potential energy is pushing it in a direction that's trying to push towards lower potential energy. Not necessarily towards the lowest possible potential energy, it's just going to push in the direction that immediately decreases potential energy. If we go back to this formula though, what is the derivative of 1/2 kx squared? Assuming that 1/2 and k are constants. So we're just taking the derivative of x squared. Yeah, x squared becomes 2x. The 2 and the 1/2 cancel out, so we get just k times x. The force of the spring, therefore, is going to be negative derivative, so that's negative kx. So that's a formula we can use for the force of the spring. The force of the spring is negative spring constant times displacement, which means, among other things, if the displacement is 0, we get no force. In other words, equilibrium is 0 force at all. If you stretch the spring to the right, x is positive. This negative sign means the force will be negative, pulling back towards equilibrium. If you compress the spring, x is negative, so the force will be positive, pushing back towards equilibrium. This is an example of what's called a restorative force. In the sense that this force is always trying to restore the equilibrium situation. If you pull something away from equilibrium, a restorative force tries to push back towards equilibrium, restoring the original situation. And those usually tend to lead to oscillation. If you pull an object to stretch the spring and let go, it's going to be pulled back towards equilibrium, keep going because of momentum, slow down, return, and it's just going to oscillate around equilibrium. So restorative forces usually tend to lead to oscillation around equilibrium. Any questions on the graphs of potential energy? All right, sounds good. Glad I could help out. Have a good weekend, and I will see you next time.